Okay, so everyone knows the Euler method, like method for approximating numerical solutions to these, and everyone knows it's a bit garbage. Okay, no one actually uses it. It's really inaccurate. But I was wondering, how can we show how garbage it is? How can we mathematically show that the Euler method will not yield satisfying solutions? And so I was looking through YouTube. I was looking at YouTube for this and couldn't really find a video. So here I am, making it myself. And for a bit of context, I'm a physics undergrad, so expect very inaccurate mathematical descriptions. Anyways, without further ado, let's get into it. So first of all, what is the Euler method? Very simple. You essentially approximate a derivative with discrete time steps. So say you have some f dots, then you can say with this that fn plus 1 equals to h f dot at some time step n plus fn. Right, it's effectively using the first order Taylor expansion for this, and just like taking it from a continuously varying function f onto just some discrete function fn. Right, so that's what the Euler method is, in case you didn't know. Now you know. And a case I found interesting was a two-body gravitationally interacting system, and yeah, it's a very neat system, mostly because you can get stable orbits with that, and any good solver would have stable orbits. But as we'll show, the Euler method doesn't really have that. So okay, first of all, we gotta write down the differential equations. So let's do that. And before that, actually, let's just have a diagram to see what we're dealing with. So suppose we have the origin here, mass 1 here, mass 2 here, and we denote the positions, the positions alpha and beta. Right, and we say that alpha dot is VA, beta dot is VB. Okay, so with that we're ready to write down the continuous differential equations. Now this is basically Newton's second law, there's nothing much to it. So then we have VA dot, i.e. the acceleration, is equal to m2g over alpha minus beta modulus of that cubed in the direction of alpha minus beta. Let's see, the acceleration's going to go that way, so yes. And AB dot is equal to m1g over alpha minus beta cubed in the direction of beta minus alpha. Right, and we also have these two equations. I'm just going to label the equations for these. So let's say that's 1, 2, 3, 4. Okay. Now that we have that, we can apply the Euler method and see what discrete equations we get. So just introducing the notation here. Let's say that alpha goes to an, beta goes to bn, va goes to capital Vn, vb goes to u, n goes to un. Okay, so we go from continuous. So let's see what equations we get using Euler. So 1 becomes n plus 1 is equal to h bn plus an. I should say we're using a time step h. Now equation number 2 is bn plus 1 is equal to hun plus bn. Now the more interesting equations, 3 becomes bn plus 1 is equal to minus an minus bn times m2g over an minus bn cubed. Now all of that times h plus bn. And similarly, 4 is n plus 1 equals to minus bn minus an m1gh over an minus bn, all of that cubed, plus un. Now it's going to be useful to introduce the relative position Rn equals an minus, bn minus an, doesn't really matter, just to make all of this neater, right? So we can write in Rn here, and minus Rn, so positive Rn here. Okay? So now this is what Euler gives us. And regularly we just stick this into Python or something and iterate a bunch of times with a small time step, and that's the solution, right? But here what we actually want to see is track a physical quantity that's going to show us how well Euler performs. And that quantity is going to be energy, you know. Now, why is energy good to track? Well, firstly, we know something about energy in the system. It should be constant. And also, we know that if energy increases, then we're not really going to get any bound orbits. The solutions are going to be unstable, right? And if it decreases, then the solutions would just spiral into a point. So knowing something about energy changes is going to tell us about the stability of solutions. Okay then, so let's see what the energy at some time step n would be. So as we know, it's the sum of the kinetic terms plus the potential terms. Now the kinetic terms are m1 bn squared over 2, where bn squared is just bn dot bn, plus m2 un squared over 2, and the potential term is going to be m1 m2 g over Rn, magnitude of that. Okay, it's all very standard physics, honestly, nothing too interesting here. Now, in a similar way, if we look at the energy at the next time step, so n plus 1 is effectively going to be all of this, but just at the next time step. Oh. So let me just copy paste that. And quickly change it. Okay, but now it's all a bit too general, right? We could write this, this expression of energy is going to hold for any method we use. Could be using Runge-Kurler for symplectic Euler, whatever, right? And this formula would be the same. So now let's actually use the fact that we're using Euler's method, right? And with that, we're effectively just going to sub in these terms, right? The n plus 1 terms. And we're going to get it in terms of un, Rn, all of that. And now this is some crunchy algebra. So algebra ensues, and we'll see what expression we get. Okay, algebra ensued. This beautiful expression is what we have. Now, it looks ugly at first, and it is ugly, it's really ugly. But there's some beauty to this chaos. So I should explain the terms. This is the kinetic energy of the MC particle. That's the kinetic energy of the M1 particle. And this term, most interesting for, is the potential energy. Now, I think it'd be worth showing how I got this term, because there's some assumptions in this. So, as you know, the term that we have for potential is this. Right. Which doesn't look very much like that. But don't fret, we'll get there. Okay, so here the only thing we can actually expand is the Rn plus 1. So let's do that. Now recall how Rn is Bn minus An. So Rn plus 1 is going to be all of that but plus 1. And using our Euler relations, we're going to get that this is Bn minus I n plus h un minus Bn. Now here I've introduced another bit of notation, delta Bn, being that, as you can see. So we'll use that to shorten notation. So this is going to be Rn minus h delta Bn. Right, so we have this for Rn plus 1. Now, the physicists among you are going to be smelling a juicy Taylor expansion. And yeah, it is good. It's a good expansion. Now, as always, every time we Taylor expand, we have to justify, right? Now, in this case, it's okay to Taylor expand because we have h. And h in numerical simulations is going to be very small. Otherwise, you're going to get a rubbish answer regardless of the method you use. Right, so we have a small h, and we can Taylor expand. Now, the only problem is that this is a vector, that's a vector, and Taylor expanding vector functions is a bit of a pain. So let's turn all of that into scalars. Now we're going to use the fact that modulus of a is the square root of a dot a. So using that, we have minus m1 m2 g, and on the inside we have this thing dotted with itself, which is going to be Rn squared plus h delta Bn squared, h squared delta Bn squared, minus 2h Rn dot delta Bn, and all of this to the minus a half. And this is where the Taylor expansion comes in. Right, so we're actually going to go to second term, and you will see why in a bit. So actually we're going to rewrite this in a more practical form, so we can use the binomial expansion, really, basically Taylor expansion. Right, now that we have that, using the formula 1 plus x to the n is roughly equal to 1 plus nx plus n plus 1, and minus 1, I should say, over 2x squared plus dot dot dot. Right, so using these three terms, we get that beast over there. Okay, so we don't really care about this anymore. So let's see, what are we actually trying to see? We're trying to see how the energy changes over time, right? Because if it doesn't change, then we're good. We can have nice, stable orbits. Euler method isn't so bad. We can model things with it. But if it does change from time step to time step, then we're in trouble. And that's what we want to see. So okay, it's going to be useful then to track this quantity, call it epsilon n, being defined as en plus 1 minus en. And when we actually compute that, we get that epsilon n is, well, this whole thing minus that small thing, and actually that. And actually, that's quite nice. This term cancels, that term cancels, as does this term. So not so bad. And actually, once you simplify further, you notice actually that the linear terms cancel as well. I.e., this term cancels with those two terms. I should say I miswrote this. There should be a h term here, and other multiplicative factors here, m1, m2, g over rn cubed h. Right, so there's a bunch of cancellations going on, which is very nice. And we're just left with the second order terms, which is why I expanded to second order. Hindsight is gold. So what expression are we actually left with? What's this beautiful thing we're left with? And well, it's going to be this. And so that's what we're left with. A bit ugly, but there's one key observation. This is not zero. You know, it's not necessarily always zero. It hasn't cancelled away like the linear terms. It's there. It's something. This is the energy difference from time step to time step. And I've stared at this for long enough, and I haven't really been able to come up with any intuitive explanation as to when this might be zero, you know, because it is going to be zero sometimes. But what matters is that in most cases, in general, it's not necessarily going to be zero. And yeah, I plotted this on Python, you know, run a cheeky simulation to see whether this formula actually holds. And it does, in fact, hold pretty well. It's a pretty high accuracy. So yeah, when we run the simulation, this is what we get. So these are the trajectories of the simulated particles. That's the total energy of the system. That's comparing, like explicitly calculating the energy difference. So at each time step, we take the position and the velocities that we calculated, and we actually compute the energy. And that's comparing it to our formula here, which is just using the theoretical values. And as you can see, it's pretty good. It's pretty good formula. Good agreement. And this diagnostic term is actually this thing I've written here. And that's just that's literally the value that we were expanding on in the Taylor expansion. So we had something like 1 plus this to the minus a half. And remember, we can only Taylor expand if this term is small. And you can see that it's pretty small. So the Taylor expansion is fittingly good. Okay, that's all. Don't subscribe, I'm not going to do any more of these. See ya.